All right, folks, our next section, we're going to get back to learning some more new calculus, section 7.2. We're going to deal with the natural, logarithmic, and exponential functions. And notice I'm calling this video part 1. The reason for that is there's a lot of information in this section, so I thought it would be best if I separated it into two videos. So in this video, part 1, we're just going to focus on the natural logarithmic function. So let's do a little review. Remember the power rule for integrals said, the integral x to the n dx equals 1 over n plus 1 x to the n plus 1 plus c for n not equal to negative 1. So at this time, we don't know what the integral of x to the negative 1 dx, or you could think of x to the negative 1 as being 1 over x. So we don't know what the integral of 1 over x dx is. We have no idea. However, our next definition, well, it begins to help us attack this unknown integral. So this definition, the natural logarithmic function, it is defined as, well, there it is, natural log x equals the integral 1 to x of 1 over t dt. So natural log x is defined as a definite integral. And in this definition, x is greater than 1, or I'm sorry, x is greater than 0, which in essence means the domain is 0 to infinity. Now, folks, there are 3 immediate facts this definition tells us, and you know what? I think we need to head off to the chalkboard so we can see what these 3 immediate facts are. So let's head to the chalkboard and see what these 3 immediate facts are. All right, folks, we've just seen how natural log is defined, and I have it up there in the upper right-hand corner of the chalkboard. The natural log x equals the integral from 1 to x, 1 over t dt, x greater than 0. So there are 3 facts we're going to come up with here just based on that definition and what we know from calculus. So here's fact 1. So fact 1 is, x is greater than 1. So x is greater than 1. This shaded region matches up with, let me call this number 1, the integral 1 to x, 1 over t dt, and that shaded region would be a positive number. So this integral is positive. So what does that tell me? Well, that tells me if my x is greater than 1, and since this is how natural log is defined, it's over there, so if x is greater than 1, natural log x is a positive number. So that's fact number 1. Fact number 2. Well, remember, x has to be greater than 0. But x could be here to the left of 1. So x could be something between 0 and 1. So what does that tell me? Well, the definite integral that matches up with that area would be the integral from x to 1, 1 over t dt. And we know that that is positive. Now if I switch the limits of integration, remember I can switch the limits of integration, but when I switch the limits of integration, I have to put a negative sign in front. So this obviously would be a negative result. So now what does that tell me about natural log x? Well, it looks like it tells me if my x is between 0 and 1, so let me write that down here. If x is between 0 and 1, then natural log x is a negative number. All right, now let's look at what I'll already label as the third one here. What if x equals 1? Well, if x equals 1, you just have a line segment here. that integral that matches up with that would be the integral from 1 to 1, 1 over t dt. And we know when the limits of integration are the same, the definite integral has a value of 0. So what does that tell me about natural log x? Well, it tells me that if x is equal to 1, the natural log of 1 is 0. Okay, so those are just 3 facts we get immediately from the definition of natural log x and using some of our calculus knowledge. So let's head back to the slides and see what we're going to talk about next. All right, so we used a little bit of our calculus knowledge to come up with 3 immediate facts from that definition. The graph of ln x is shown here to the right. So the blue graph, that's the graph of natural log x. And besides incorporating the facts we just saw on the chalkboard, here are some more facts about natural log x. Fact 1, the domain is 0 to infinity. The range is all real numbers, negative infinity to infinity. I mean, just looking at the graph of ln x, the function is continuous on its domain. The function it's always increasing, and the function is 1 to 1. Also, looks like the graph is concave down everywhere. Tangent lines to the graph would be above the curve. And a couple of calculus facts. As x goes to infinity, so the limit as x goes to infinity of ln x, that limit is infinity. And the limit as x approaches 0 from the right side of 0, it's the only side we can approach 0 from, of ln x, well, that limit is negative infinity. So these are facts, but a question I have, how do we actually show that f of x equals ln x is increasing? And how do we show that the graph of f of x equals ln x is concave down? Well, we know the answer to that question. We need the derivative. That tells us where a function is increasing or decreasing. And we need the second derivative. That tells us concavity. But now, since ln x is defined to be ln x equals the integral from 1 to x of 1 over t dt, we know that the derivative of ln x, look, I'm just going to differentiate with respect to x, both sides of the equation. We know what the derivative of ln x is, because on the right side here, when we ddx the integral from 1 to x, 1 over t dt, we employ the power of the second fundamental theorem of calculus. So we know that it is 1 over x. When you ddx the integral 1 over x, 1 over t dt, the second fundamental theorem of calculus tells us you immediately get 1 over x. So that's thanks to the second fundamental theorem of calculus, which means we have a new derivative rule. We now know the derivative of natural log x is 1 over x. So let's put that in a theorem. So this theorem is going to have 3 parts to it. Part 1, the derivative of ln x is 1 over x. Now part 2 is kind of like the chain rule part. So if u is a differentiable function of x, not equal to 0, the derivative of natural log u is 1 over u times du dx. So the derivative is 1 over whatever this is times the derivative of this. That's the chain rule. And then part 3, if u is a differentiable function of x not equal to 0, when you ddx the absolute value of u, well, that derivative is also 1 over u times du dx. Now, there's something brewing here in part 3 of the theorem. So to see where part 3 of this theorem comes from, let's make a quick trip back to the board so we can analyze that. All right, we've added a new rule of derivatives to our arsenal, and it's the derivative of natural log x is 1 over x. And in part 3 of the theorem, we had the derivative with respect to x, natural log absolute value of u, where u is a differentiable function of x, equals 1 over u du dx. And I said I was going to make a quick trip to the board to kind of explain why it looks the same as rule number 2. I also put up on the board a friendly reminder on how absolute value of x is defined. So I'm going to look at this as cases. So case 1. If x is a positive number, then the derivative with respect to x of natural log x is just 1 over x. That's our new rule. That was part 1 of the theorem. Now, if x is less than 0, well, we know negative numbers are not in the domain of natural log x. So I would have to ddx the natural log of the opposite of x. If this is negative, I'd have to, the opposite of a negative would be positive. So let's get the derivative of this. Well, the derivative is negative 1 over x times, now the chain rule. The derivative of negative x is negative 1, which gives us 1 over x. So this together, putting it together, tells me, I guess one would say it actually tells me the derivative with respect to x of the natural log absolute value of x is 1 over x. But if we have a differentiable function of u, the structure doesn't change. So I just kind of wanted to do a very brief explanation of why part 3 of the theorem is as it's written down. So let's head back to the slides and see what we're going to do next. Probably an example. All right, so what led us down this path was how do we know that natural log x is increasing? And how do we know that natural log x, the graph of natural log x, is concave down everywhere? Well, for the function ln x, we now know the derivative is 1 over x. For any value of x you can think of greater than 0, f prime is also going to be greater than 0. And if f prime is greater than 0, that means the function is increasing. And for the function ln x, since we now know the derivative is 1 over x, we know the second derivative is negative 1 over x squared. And again, for any value of x greater than 0, the second derivative will always be negative, which means the graph of ln x is concave down everywhere. Okay, I'm going to give you this is just a review from algebra. So these are some facts from algebra. Natural log of 1 is equal to 0. We actually saw that earlier in the slides. Number 2, you may remember this as people call them like laws of logarithms. But it says if you have the natural log of a product, so the natural log of x times y, you can rewrite that as addition. So natural log of x times y equals the natural log x plus the natural log y. Number 3, the natural log of the quotient, x divided by y, equals the natural log of x minus the natural log of y. And the fourth one is if you have the natural log of x to the p, you could rewrite that as p times the natural log of x. Now here are some calculus facts. Well, we know the first one, the derivative of natural log x is 1 over x. The derivative of natural log absolute value of x is 1 over x. The derivative of natural log absolute value of u is 1 over u times du dx. It's the chain rule. And then the fourth fact is something we get for free. Since we know the derivative of natural log absolute value of x is 1 over x, for free we get the integral of 1 over x dx is the natural log absolute value of x plus c. So that fourth fact kind of fills in that missing item for the power rule. We now know what the antiderivative of 1 over x is. It's natural log absolute value of x plus c. All right, now I think it's time we do some practice on computing derivatives. So let's look at this example. Going to have 4 parts to this example, so make sure you write down all 4 parts because you know I'm going to head off to the chalkboard and I'm going to work through them, and I'm even going to ask you to do a couple, you know, after we work through each part of this example. So here I go, off to the chalkboard. All right, example of differentiating with our new derivative rule. Part A, the function is natural log of x squared plus 3. So we use our new rule. We get the derivative is 1 over x squared plus 3 times, now the chain rule, the derivative of x squared plus 3, which is 2x. And yeah, I could write it like this. Not too bad. Part B. Just because we've learned a new rule doesn't mean it's okay to forget the old rules. I mean, look, you have a product rule here. You have x times ln x. It's the product of 2 functions. So the derivative is, we're going to have to use the product rule. So let's see, the derivative of the first function is 1 times the second function plus the first function times the derivative of ln x is 1 over x. And yeah, I would simplify it to that. It's not much simplifying. Part C, I could just start off using calculus. You know, the derivative would start off 1 over x plus 1. And then times, you know, the chain rule, doing the derivative of x over x plus 1, that would require me to use the quotient rule while I'm using the chain rule. But there's a much easier way to do this derivative. If we take advantage of a law of logarithms, if we take advantage of the fact we have the natural log of a quotient, and we just make algebra the first step, rewrite the natural log of the quotient as the difference, ln x minus ln x plus 1. Then the calculus is just one step that isn't bad. The derivative of ln x is 1 over x. The derivative of ln x plus 1 is 1 over x plus 1. Well, and then chain rule times the derivative of the inside function. Well, the derivative of the inside function is 1. That's it. So one little step of algebra made the calculus a lot easier. And, oh, there's a part D. Almost forgot, so bear with me. Let me erase some stuff here so I can get part D up here on the board. So part D, see, your function is natural log absolute value of sine x. Well, I guess the derivative just starts off 1 over sine x times the derivative of sine x, which we know is cosine x. And I would actually write my derivative as cosine x over sine x, or even better, cotangent x. And I would feel awful if I didn't mention this right now. Notice that for free, you now know the antiderivative of cotangent x. The antiderivative of cotangent x is natural log absolute value of sine x. And that's for free. Remember, they're inverse operations, integration and differentiation. So, you know, I have a few I'd like you to try here. So go to the exercises. Section 7.2 exercises. Pause the video. 7.2 exercises. Do 18, 22, and 28. Once you're done with those, restart the video and I'll be here working through them and hopefully you have correct answers. Alright, number 18, you're asked to differentiate with respect to x squared, natural log x. So you use the product rule. You have two functions multiplied together. So in using the product rule, we would get the derivative of the first function times the second plus the first function times the derivative of the second. And you can quickly simplify this to, x squared times 1 over x. That's just x. So that was it for 18. 22, the derivative with respect to x, natural log x squared over x. No way around this one. We have to use the quotient rule. So here we go, quotient rule. Quotient rule says the derivative of the numerator. Well, that's 1 over x squared times 2x. Don't forget the chain rule. So that's the derivative of the numerator times the denominator minus the numerator times, the derivative of the denominator is 1, and that's all over the denominator squared. So this is just screaming to get cleaned up a little bit. Look here. We know 2x times x is 2x squared. So 1 over x squared times 2x squared leaves you with just a 2. That wasn't too bad. And I suppose if you wanted to, you wanted to show off your algebraic prowess, you could use a law of logarithms and rewrite natural log of x squared as 2 times the natural log x. Either one of those would be fine, folks. Alright, 28. The natural log of cosine squared x. Oh, we're going to have a fun time here. So we start off the derivative. Okay, we have the natural log of cosine squared x. So it starts off 1 over cosine squared x times. Now we have to do the derivative of the inside. The derivative of cosine squared x. Remember cosine squared x really means cosine x quantity squared. So when we differentiate that, we get 2 cosine x, and then we have to do the derivative of cosine x, which is negative sine x. So we're going to do some simplifying here. We could at least write it as a negative 2 cosine x sine x over cosine squared x. And this cosine x would cancel out with one of those cosines, so we'd have a negative 2 sine x over cosine x. And we know sine over cosine, we know that's tangent. And that's a good answer there. So, hopefully you're able to get these three, 18, 22, and 28. Let's head back to the slides and see what's next. All right, now that we know how to do derivatives, now it's time to integrate. So here are 2 examples. Make sure you write them down. You're going to see, back when we learned U substitution, I gave you some guidelines for U substitution, and I told you at that time guideline 2 and guideline 3 would be important when we did the next chapter. Well, here we are. This is the next chapter. So you're going to start to see some U substitution, and I'll harken back to the guidelines that I presented in an earlier video. But in any event, write these down because I'm going to head off to the chalkboard and work through them. All right. Doing a little integration now. So let's look at the first one. integrate x squared over 2x cubed plus 1 dx. So we're going back to use substitution. I gave you some guidelines in section 5.5 on use substitution. I said at that time, guidelines number 2 and 3, you would start to worry about them in a future chapter. Well, now is the future. So if I think back to those guidelines, one of the guidelines was try letting u equal the denominator. So u equals 2x cubed plus 1, which means du is 6x squared dx. So when I substitute in, my denominator's u, and then I still have this x squared dx to take care of. Well, 1/6 du, that equals x squared dx. So I substitute 1/6 du in for x squared dx. I'll take the 1/6 and rip it out front. Now we have a friendly integral to do. This is just 1/6 natural log absolute value of u plus c. 1/6 natural log absolute value of 2x cubed plus 1 plus c. Part B. Well, looks like candidate for u substitution, so let's let u equal the denominator. Then du would be a negative sine x dx. Or kind of looking ahead, negative du is sine x dx. So I substitute in, denominator's u, the sine x dx, I substitute negative du for that. I put the negative 1 out front, and then remember, definite integral, u substitution, there are two routes to go. Either route 1 was you leave the limits of integration off, because remember these limits pertain to the variable x. So you leave the limits off, get an antiderivative, resubstitute, use the original limits. Or route 2, change these x limits, change them to u limits. And you know, excuse me, it does not matter at all which route we go, route 1 or route 2. So I'm going to go route 1. I'm just going to leave it as is. Get my antiderivative. Negative, natural log, absolute value of u. Resubstitute. So that gives me a 1 plus cosine x. Bring back the original limits of integration. So I have negative natural log, absolute value 1 plus cosine pi over 2 minus negative natural log 1 plus cosine of 0. Alright, cosine of pi over 2 is 0. 1 plus 0 is 1. The natural log of 1 is 0. So all of this becomes 0. Minus a negative is plus. So let's see, cosine of 0 is 1, so 1 plus 1 is 2. So that gives us the natural log absolute value of 2, but we know absolute value of 2 is just 2. So the answer for part B is natural log of 2. Alright, so I want you to practice a couple of these integration problems. So here in the section 7.2 exercises, pause the video, do numbers 42 and 46, and as always, once you've done them, restart the video. I'll be here at the board working through them. Alright folks, number 42, you're asked to integrate 1 over 4x minus 3 dx. Hopefully you let u equal 4x minus 3, then du is a 4 dx. You substitute in the u statement, and you look and you say, well, all I have left is a 1 dx. So that means 1/4 du is 1 dx. So you substitute 1/4 du in for the 1 dx. Rip the 1/4 out front. Very friendly integral. And then you resubstitute. And hopefully this is what you ended up getting. All right, now we're going to develop a rule here that's going to help us get antiderivatives that look like this in just one step, that we don't have to go through all this work. So here it is. I'm using this as motivation for what if I have the integral 1 over mx plus b dx. So I'm basically saying the denominator is a linear function. Don't know what m is, don't know what b is. It's just a linear function. Well, we can do this. We can let u equal mx plus b. Du is just m dx. We substitute in, we get a 1 over u du, where 1 over m is equal to dx. So we get 1 over m, natural log, absolute value of u plus c. That's 1 over m, natural log, absolute value, mx plus b plus c. So we have just developed the following rule, if you will. The antiderivative of 1 over mx plus b equals 1 over m, the natural log of mx plus b plus c, and of course that's true for m not equaling 0. So how could I extend this new rule that we have just developed? What if I solve this? What if I solve the antiderivative of a over mx plus b dx? Well, I think since a, you could rip a out front, it's just going to be a times this integral. Well, a times this integral means it's a times this antiderivative, which gives us a over m, the natural log, mx plus b plus c, where again, m does not equal 0. Folks, this is going to save you a lot of time in the future. I mean, for example, right now, if I'm asked to integrate 1 over 7x plus 2 dx, I can get this antiderivative without doing any work. It's 1 over 7 natural log absolute value 7x plus 2 plus c. Boom, done. So number 42, it kind of served as motivation for us to maybe develop a couple of extra rules that will pay off in the future, trust me. You had one more that I asked you to do, number 46. So let me get number 46 up here on the board. So let's see, it was, ooh, that's a good one. Integrate secant squared x over tangent x dx. And I noticed that if I let u equal the denominator, du is secant squared x dx. And so when I substitute in, my denominator's u, and secant squared x dx is exactly equal to du. I mean, that rarely happens. Very friendly antiderivative. Resubstitute, and we are done. Hopefully you got this. So, a little bonus information based on number 42. We got a couple of new little sub-rules, if you will. I don't know if you'll find those in the book or not, but hey, that's why I make a video. So, we're almost done with part 1 of section 7.2. Let's head back to the slides and quickly finish this off. All right, folks, this ends section 7.2 7.2, the part 1 video. So from the exercises that I listed for section 7.2 on the academic calendar, you can now do from that list 17 through 29 odd, 41, 43, 45, 49, and 79. So I would encourage you to do these exercises in section 7.2 because it matches up with this video. Thanks for watching.